This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on the groundbreaking paper, Attention is All You Need. This research introduces the transformer, a novel neural network architecture based solely on the attention mechanism, abandoning recurrence and convolutions entirely. Let's begin by discussing the limitations of traditional sequence transduction models that the transformer aims to overcome. What were the primary shortcomings of the existing recurrent and convolutional approaches?
Traditional sequence transduction models, heavily reliant on recurrent neural networks, RNNs, like LSTMs and GRS, suffer from a fundamental limitation: sequential computation. Processing input sequences element by element inherently restricts parallelization during training, significantly impacting efficiency, especially with long sequences. Convolutional approaches, while offering some parallelization, struggle with capturing long-range dependencies effectively, as the computational cost grows with the distance between positions.
So the sequential nature of RNNs and the distance-dependent cost of convolutions were the major bottlenecks. How does the transformer architecture address these issues?
The transformer's key innovation is its exclusive reliance on the attention mechanism. This allows for significant parallelization because the attention mechanism can process all input positions simultaneously. Furthermore, the self-attention mechanism directly models relationships between all positions in the input sequence, regardless of their distance, overcoming the long-range dependency problem inherent in RNNs and convolutional networks.
The paper highlights the superior performance of the transformer on machine translation tasks. Can you elaborate on the specific improvements achieved and the reasons behind them?
The transformer achieved state-of-the-art results on the WMT 2014 English to German and English to French translation tasks, surpassing existing models by a significant margin, over 2 blue points in English to German. This improvement stems from the increased parallelization, enabling faster training and the ability to capture long-range dependencies more effectively, leading to better translation quality. The reduced training time is also a significant advantage.
The transformer utilizes a multi-head attention mechanism. What is the rationale behind this design choice, and how does it contribute to the model's performance?
Multi-head attention allows the model to attend to information from different representation subspaces simultaneously. Instead of a single attention mechanism, the model uses multiple attention heads, each focusing on different aspects of the input. This enables the model to capture richer contextual information and improve the overall representation learning. The computational cost is comparable to single-head attention with full dimensionality, making it an efficient choice.
The paper also mentions positional encoding. Why is this necessary in a model that lacks recurrence and convolution, and what method was employed?
Because the transformer lacks inherent sequential processing, positional information needs to be explicitly provided. The paper uses sinusoidal positional encodings, where each dimension of the encoding corresponds to a sinusoid with a different frequency. This allows the model to easily learn to attend by relative positions and potentially extrapolate to longer sequences than seen during training. Learned positional embeddings were also explored, yielding similar results.
The paper explores various model variations. What were some of the key findings from these experiments regarding the impact of different hyperparameters and architectural choices?
Experiments showed that the number of attention heads and the key value dimensions significantly impact performance. Too few or too many heads negatively affect results. Increasing model size generally improves performance, but dropout regularization is crucial to prevent overfitting. The choice between sinusoidal and learned positional encodings had minimal impact on performance.
Beyond machine translation, the transformer's applicability was demonstrated on English constituency parsing. What were the results, and what does this suggest about the model's generalizability?
The transformer achieved competitive results on English constituency parsing, even outperforming existing models in low data regimes. This demonstrates the model's ability to generalize to other sequence tasks beyond machine translation, highlighting its versatility and potential for broader applications.
The paper concludes by discussing future research directions. What are some of the promising avenues for extending and improving the transformer architecture?
Future research could focus on extending the transformer to handle various input-output modalities beyond text, images, audio, video, exploring local or restricted attention mechanisms for efficiency with large inputs, and developing methods to make generation less sequential.
The paper mentions the use of atom optimizer and specific regularization techniques. Can you elaborate on the role of these choices in the training process and their impact on the final results?
The atom optimizer was chosen for its efficiency in optimizing the model's parameters. The learning rate schedule, with a linear warm-up phase followed by an inverse square root decay, helped stabilize training and improve convergence. Regularization techniques, including residual dropout and label smoothing, were crucial in preventing overfitting and improving generalization performance. Label smoothing, in particular, improved accuracy and blue score despite hurting perplexity.
The attention visualizations in the appendix are quite interesting. What insights do they provide into the model's internal workings and the nature of the learned representations?
The visualizations reveal that different attention heads learn to perform different tasks, some focusing on long-distance dependencies, others on anaphora resolution, and still others on aspects related to sentence structure. This suggests that the multi-head attention mechanism allows the model to decompose the complex task of sequence transduction into smaller, more manageable subtasks.
The paper mentions the use of byte pair encoding and word piece modeling for tokenization. How do these techniques contribute to the model's performance, and why were they chosen over simpler methods?
Byte pair encoding and word piece modeling are subword tokenization techniques that handle rare words and out-of-vocabulary tokens more effectively than word-based tokenization. They create a shared source target vocabulary, improving the model's ability to learn relationships between words across different languages. This is particularly beneficial in machine translation, where rare words are common.
The paper provides a detailed comparison of self-attention with recurrent and convolutional layers in terms of computational complexity, parallelization, and path length for long-range dependencies. Can you summarize the key findings of this comparison?
The comparison highlights self-attention's advantages. Constant computational complexity per layer regardless of sequence length, compared to linear for RNNs and logarithmic for ByteNet, maximum parallelization, sequential operations, and short path lengths for long-range dependencies, O1 compared to ON for RNNs and O low key for dilated convolutions. This makes self-attention particularly well-suited for handling long sequences.
The paper discusses the use of beam search during inference. What is beam search, and how does it contribute to improved translation quality?
Beam search is a heuristic search algorithm that explores multiple possible translation hypotheses simultaneously. Instead of greedily selecting the most likely word at each step, it maintains a beam of K hypotheses, expanding each one and selecting the best overall hypothesis at the end. This helps to avoid getting stuck in local optima and improves the overall quality of the generated translations.
The training data and batching strategies employed are also important. Can you describe the data sets used and the rationale behind the batching approach?
The paper used the standard WMT 2014 English-German and English-French datasets. Sentences were encoded using byte pair encoding, English-German, and word piece modeling, English-French. Batching was done by approximate sequence length to improve training efficiency and reduce memory requirements.
The paper mentions the use of layer normalization. What is layer normalization, and how does it contribute to the stability and performance of the transformer?
Layer normalization normalizes the activations of a layer across the feature's dimensions rather than across the batch or time steps. This helps to stabilize training, particularly for deep networks, by preventing the vanishing or exploding gradient problem. It also improves the model's performance by allowing for faster convergence and better generalization.
The hyperparameters used in the training process, such as dropout rate and label smoothing, are carefully chosen. Can you discuss the impact of these hyperparameters on the model's performance?
The dropout rate controls the amount of regularization applied to the model, preventing overfitting. A higher dropout rate leads to more regularization, but can also hurt performance if it's too high. Label smoothing reduces the model's overconfidence in its predictions, leading to improved generalization and robustness.
The paper estimates the training cost in terms of floating point operations, FLOPs. Why is this a useful metric for comparing different model architectures, and what were the key findings regarding the training cost of the transformer?
FLOPs provide a standardized measure of the computational resources required to train a model. Comparing FLOPs allows for a fair comparison of different architectures, even if they are trained on different hardware or for different durations. The transformer demonstrated significantly lower training costs compared to existing state-of-the-art models, highlighting its efficiency.
The paper mentions the use of residual connections. What is the purpose of residual connections in the transformer architecture, and how do they contribute to its effectiveness?
Residual connections allow the model to learn identity mappings, making it easier to train very deep networks. They help to alleviate the vanishing gradient problem and improve the flow of information through the network. This is particularly important in the transformer, which uses a deep stack of encoder and decoder layers.
Let's revisit the overall architecture of the transformer. Can you provide a concise summary of the key components and their interactions?
The transformer uses an encoder-decoder architecture. The encoder processes the input sequence using stacked layers of self-attention and feed-forward networks. The decoder similarly uses stacked layers, but also incorporates decoder attention to attend to the encoder's output. Positional encodings are added to handle the lack of sequential processing. The entire architecture is highly parallelizable due to the attention mechanism.
This has been a comprehensive discussion of the Attention is All You Need paper. Thank you for your insightful explanations.